Good afternoon, Professor.
Hello. Oh, wait a minute. Wait a minute.
Described as sort of a redshift
hang on.
for sound. I don't know if
Hold
everybody.
on.
I'll repeat that. I'll repeat that.
Yeah,
Some
top of the afternoon. Hold on. Something's happening.
As a sort of a redshift,
Hold on.
but for sound. Well, the
Yeah,
simple
sound
answer
is weird. Yes.
absolutely
Hold on
yes.
one
Now, I
second.
don't know if everybody knew those. But it's a good question, and the answer is yes. I would back up. Well, I'll say more about that, but great question. But the answer is yes. Then what's the deal? Okay, I'm gonna switch. I will go back to this page. I promise you, this page might look like sort of what.
Okay. Let's see. Hold on. Good afternoon. Yes. Good afternoon. Okay. Sorry. Another crazy start. Second coming. Hello. Good afternoon. Yes. Okay. Let me start again. Sorry. This is I have so many apologies, but I'm not going to spend the whole class on apologies, but please accept a million apologies right now. Okay. If you said good afternoon already vocally, I didn't hear because my sound was all messed up, but I'm just going to guess and say hello to Amy and hello to who are the people that usually say, and Sarah, and Jamalette. But now, yes, hello, good afternoon, Olsmail, good afternoon, Samuel, good afternoon, Sophia, good afternoon, good morning, Jalen, good afternoon, Diana, hi, Sarah, good afternoon, Jamalette, top of the afternoon, Abdel, good afternoon from 2D, Stephen, good afternoon, Brooke, good afternoon, Brianna, yes, the sound was weird, I hope it's fixed now. It was two of me coming out on one, anyway, good afternoon, Nicholas, good afternoon, Shakia, good afternoon, Jasmine, good afternoon, Dave, good afternoon, whoa, oh, thank you, okay, good, wait, no. Good afternoon, what did I just say? David, good afternoon, Amy, good afternoon, Chloe, oh, thank you, private chat person who's telling me about the sound. Okay, good. Thank you. And someone else is here, and we're gonna get rolling. Okay. Obviously, so I owe you a million apologies. I was out on Monday unexpectedly. This has been and I was out. Yeah, I didn't come to campus yesterday when I might have wanted to visit with some of you, or you might have wanted to visit with me. I wasn't there at all for the last 2 days. I apologize. I think all is fine. Just weird things are happening on my end. I apologize. There's no secrets, but it's not worth going into right now. I'm happy to talk to any of you about, outside of class, but I do apologize. I've been a little bit distracted and distractible. We're going to get back to class material right now. Also, so I think you saw on the Google stream, I've obviously been very behind and slow on these exams. There's no excuse. It's not good. I just wanted to make clear to you in the stream that they've started to come back now. Like the machine was really slow for a while. Now the machine is running. So, okay, wait, there's something in the direct chat. Hold on. Okay. Okay, thank you, direct chat. There's only one person in the direct chat. So if you're in the direct chat, I totally see it. Thank you. Totally understood. I appreciate the communication. All good. So the exams are starting to come down. I think I might have done this with you guys last semester. No problem. I'm now that like the machine is going and I had all the solutions made up and whatever, now as I finish them and put numbers on them, they're just going out. I'm not waiting for all of them to go out. So they're just going out in dribbles one at a time. Most of you have not. If you didn't get one back yet, that means nothing. I'm doing it in random order on purpose. It doesn't mean anything. Most of you have not gotten them back, but just some of you have, just to indicate that like the process is happening now and you'll get them whoever you are, you should get it any day now. I hope, I believe it's a priority. Should have been a priority long. I'm not going to spend the whole class talking about it, but I do understand how frustrating it is for you. And as I indicated in the stream, you have no new work due to me. The only thing we're all trying to do is catch up with the bulk of the work that's already been done this semester. There's very little left time in the semester. I know that. We're not going to talk about the final exam or anything until we have all this resolved. The final exam will be shorter than the last exam was. Like you're already over the hump. That's really what I'm trying to say. The final exam largely, by the time you take it, you'll know what your grade was on the midterm. And if you think you're in trouble in this class, if you're not happy with your grade, then the final exam will be an opportunity to do better and rectify. As I've done in the past, I'm just saying this right now, especially because I'm taking a while with these. I'm going to say this once clearly. I'll put this in the Google Classroom too, just so you know. You take the midterm exam and then you take the final exam. I know because it's much more helpful to you to have the feedback on the midterm, as early as possible so that you can prepare for the final, because I know that one thing I'm going to do again this semester is whichever of those two exams you do better on will count more. And I did do that last semester. I don't know if it was in your class or in two. I'm pretty sure I did it in your class. But so in other words, if it turns out you did fine on this midterm, then fine. You don't have to go through all this pain to quite the same level again on the final. It'll be shorter and the midterm will count for you more. Like you can bank your success on the midterm. If it turns out you didn't do badly, you didn't do so well on the midterm, then the final will be an opportunity for you to do better and will count more for you, assuming you do better. And again, but we've done the bulk of the material. Like it's not like it's half and half in terms of the material covered. Anyway, I'm going to stop. That's the deal. I do apologize. I just want to make that clear. I know it's, wait, okay. I'm looking at chat. But now I'm going to go on with the material, and the material, by the way, there's this one homework assignment that many of you have already turned in, which is amazing. And some of you haven't. I'm going to finish going over that homework right now. I'm going to turn the page. I'm going to go over that homework right now. Wait, I'm going to look in the direct chat in a second. I see there's something, but I want to go over. I'm going to continue helping you solve that last homework assignment that was assigned, and it is the last one of the semester. If this changes any answers that you've already submitted, by all means, re-upload and get a higher number. If you got stuck and you need this to help you, same deal. Hopefully this will help all of you understand that. And the problem I'm about to go over today usually is one of the couple of problems on the final exam. I think I've mentioned that. All right, so I'm going to go to it in a second. Just there's something in the direct chat. Oh, wait, there's a fair question in the direct chat. Hang on a second. Huh. Okay, it's kind of funny too. I mean, it's not funny, but I'll say this quickly again, because and more questions like this are very fair. I know it's frustrating to not know, what's going on. So someone put in the direct chat, what grade on either exam qualifies as not doing well, or is that left to our interpretation? So that's a cleverly put in. So I'm not trying to be evasive. In part, it is left to your interpretation in the sense that, in part, what I mean is, if you're doing worse than you want to in the class, like if you're striving for an A, but it looks like you're going to get a B, that would, for you, constitute not doing well. But, and people have different standards, but no, okay. But to be more clear, I will give you an exact answer to that once I have them all done and I know the mean score. Really, if you're anywhere near the mean on the exam, you're fine. In my opinion, in terms of your letter grade, you'll be fine. If you're like 10 points below the mean, then you may have a concern, because that would mean if you're like 10 points below the mean on the midterm exam, then if it weren't for the final, then it's true you could be heading to something like, then your grade might be for the semester, might be something like in the C range, which I presumably a lot of you don't want. What I'm really trying to say, put another way, is if you're like got near the mean or higher on the midterm when you get it back and you look at it, and I'll tell you the mean when you get it back, but if you get near the mean or higher, which probably likely means if you're like in the mid 70s or something like that or higher, again, this is now a guess because I haven't finished them yet, right? So, but like if you're like higher than the mean or in the 70s or higher, you're probably in B range. You're assuming you've been doing any homework at all and game turns, assuming you've been submitting for any other kind of extra points on any kind of regular basis, and assuming that you're fine in lab, right? Then even to be somewhere in the 70s or something like that in the exam or near the mean, probably means you are at least in like B range. I mean, I'm not trying to be vague. I also can't be exact until but the whole point of all of the other things you do in the class, all the different types of homework and the lab, is to basically say that anybody who really just does the work and hasn't checked out and is staying with the material, even if they get a sort of uncomfortable number on the midterm, like something in the low 70s that looks like a C minus, they're probably still getting a B in the class. I hope that's a little bit. So you just, if you're like 10 points below the mean, that's where you might start getting concerned. And that's where I'll reach out to you. And that's the last thing. I mean, it's a very fair question. I may be the direct chat person, and especially now, since you're all maybe a little bit anxious, which I don't want you to be, the direct chat person can tell me if I've even addressed it at all. And other people can put things like that in the chat. Of course, I can be more specific once you actually get your exam score back. But the other thing I can say that's, and I'm intentionally not looking at the chat for 1 second. The other thing I can say that was also true in Physics 203, whether it applied, whether you knew it or not, or whether it applied to you or not, is once you finally get these midterms back, especially since we're so close to the end, and I know that, if I think you have an issue in this class, like if I think, especially if I think you're heading toward a D or an F, I will reach out to you. C, okay, maybe I will, maybe I won't. Like if you think you might be in a C, you might want to reach out to me. But just to remind you, and I'll tell you this again in like 3 weeks when it comes time for the final exam, like nobody in this class is going to just suddenly be surprised to find out on CUNY first for the first time that they're getting a D or an F. Like for what it's worth, that does not happen. If I think that you're getting a D or an F, and worst, if I don't realize it or see it until you take your final exam, like if suddenly your final exam makes you have a D or an F, and I know there's at least one, I know there's people in the room right now who know what I'm about to say, like I will reach out to you and I will give you an incomplete. And that means reach out to me so we together can solve the problem. No, I'm not saying no one ever gets D's or F's. They do. But I'm saying you won't just be surprised. You won't find out for the first time on CUNY first that you're getting a D or an F without any chance to do something about it first. That I am telling you. C is like the more questionable borderline. I know nobody wants a C, but I don't necessarily reach out to people for C's because it is, it's more respectable actually than some of you think. So if you have a question, I mean, again, I'm not trying to over talk about this, but you deserve as much information as I can give you. When you get back to midterm, if you think, this looks like I might be heading for a C, like I got a 71 or I got a 66 and he said the mean was a 72, like, okay, then reach out to me and we'll see what's what and we'll see what you have to do on the final and stuff. The goal still for all of us is to get you all to do well. And the goal is for nobody to be surprised or for nobody not to have a chance to solve as they go. And I realize that getting your midterm back late makes that more challenging. Okay, I'm just going to look. Yeah, okay, so I'm looking at I have a million times. Okay. Okay, so I'll stop. All right, so someone said I made that clear a million times over. Okay, I apologize. I'm overcompensating, I'm sure. But now someone else is, yeah, so someone wrote, so ideally slightly above the mean to get an A. I mean, to be really honest and really conservative, just to be really safe, you want to be more than slightly above the mean. But if you're above the mean, if you're like noticeably above the mean, yeah, then you're in, and assuming you've been doing all these, and this is generally the case, assuming you've been doing all the homeworks and stuff, and assuming you're fine in lab, then if you are noticeably above the mean, then you are in A land, probably. And, that for some people that might include A minuses. I'm not, I don't want to raise false expectations, but yes. Okay. I'm going to pause for a second. Okay. Oh, okay. No, okay. Thank you, direct chat person. Okay. I appreciate it. I'm being very defensive. Thank you, direct chat person who's talking about the million times over and stuff. Okay. Totally. But thank you. And thank you all for understanding. Again, look, the other thing, and maybe I've made this clear too, look, I know physics is already hard enough, period. And then it's even harder with anything that the professor adds to the equation to make it harder. In my case, hopefully you all kind of, I think you do know at this point that I never try to make anything harder than it already is. But there's things built in, like the fact that I'm late with this stuff, that does not make your life easier. All I can say is I know that, and then that fact, my awareness of that is built in to my grading system and the way I look at things and the way I'll look at each one of your numbers at the end, like, believe me, the more my delays are making it hard for you, even just hard for you to stay calm. Like, the more I'm aware of that and the more that is built in to the way I calculate and report the final outcomes. Like, that just, it is. I whatever I do, I'll do for everybody too. Like, you know what I'm saying. So, but I just want you to know, I know it doesn't help to not have your exams back. I know. Okay. All right. So you can keep these comments, you know, and you can text me privately or email me privately, but I am now moving on. They are a big priority. I'm moving through them now, you know, fluidly, hopefully just they'll come in one at a time. And again, it's random. And so when you don't get one, it doesn't mean anything. It just means I haven't done yours yet. Okay. I'm going to switch the screens, but thank you for being so understanding, all of you. And I will be in my office next Tuesday for what it's worth. I'm going to switch the screens. Wait, what am I doing? So I'm going to go back to this homework thing. I'm going to, in fact, hold on. What I'm talking about, what we're going over now. I'm trying to okay, here we go. Okay. So we are going to this. Okay. I'm about to go over part B. I'm debating about whether to share the screen or not, but I think not, because I'm just about to write out. I'm going to part B, E fields from point charges. Okay. And here's the situation. You have this coordinate plane. Okay. And I can't, if there's something in the chat or anything right now, I can't see it just yet because I'm drawing. I'll switch back in a second. But so you have this coordinate plane. This is the origin. And you've got these two charges, 2 point charges. Okay. One. Oh. Okay. One is like around here. One is a positive charge. At the coordinate 5, 4. And the other is a negative charge at coordinate. I don't know why they're both in the positive, but whatever. Over here. Okay. Okay, everybody can see me. Okay, so this is the situation, right? You've got these two charges, one's positive, one's negative. They're somewhere in the XY plane. When I say they're point charges, what again I mean is so for example, the 5 coulomb positive charge is a whole bunch of protons all jammed together into a tiny volume of space, into essentially an infinitesimal volume of space. But it's a whole bunch of protons. Truthfully, it's probably like 80 quintillion protons jammed into a tiny space, because there's about 16 quintillion protons per each 1 coulomb of charge. A coulomb of charge is a great amount of protons. And so then the other is, in effect, a whole bunch of electrons, maybe like 32 quintillion electrons jammed into an infinitesimal space. That's what we're supposed to be picturing here. And as you know, that's very hard to picture. I mean, protons already are hard to picture, and that because they're so small. But then, ironically, picturing 80 quintillion of them is hard to picture for a whole different reason. And then having them all jammed into this tiny space is really hard to picture. But so it's really hard to picture. But it's just that. I'm going to keep saying that. It's just that. Really hard to picture. These are realistic numbers, and these are accurate numbers. And the whole idea is that it's, protons and electrons are really, really small. So in fact, it does take a huge, enormous amount of them to gather up and constitute a measurable a measurable amount of charge that actually has an impact on our macroscopic material world. Okay, so you got this bunch of protons over here, and you got this bunch of electrons over here. And what we want to know in this problem, again, this is homework 6 or whatever it was called, this is the second part of the most recent homework. We want to know, what is the electric field at the origin of this coordinate system, at the point of interest, at the field point 0, 0? That's our question, right? So I'm not going to write. So we want to know, like, given all the above, we want to know what is the E field vector at the point of interest, or the field point. I should really write, okay, actually. Now, what does that mean? I'm going to turn to the next page and say, what does that mean? It means we want to know the force waiting to happen. Really, we want to know the net electrostatic force waiting to happen at the point in space 0, 0. What do I mean waiting to happen? I mean, we want to know the magnitude and the direction of the force, the net electrostatic force of repulsion or attraction that will be exerted or would be exerted on each and every hypothetical positive 1 coulomb of test charge that could be found at 0, 0. I'm going to write that out mathematically in a moment, but this is the conclusion or this definition that I'm about to use for the first time is the definition that we established 2 weeks ago, last class. What I'm saying is this. I'm saying okay. What I'm saying, and obviously we're going to do, the point of today is that we're going to do this calculation, which is a somewhat thick calculation. What I'm saying is we believe that that every 1 source charge in the universe exerts an electrostatic force on any and every other test charge in the universe. If I'm a point charge over here, I exert a force of attraction or repulsion on any second charge over here. 1 proton pushes on each and every other proton in the universe. Each proton pulls on each and every other electron in the universe. There's an automatic pull or push between any two dots of charge in the universe, just like there's an automatic pull between any two dots of mass in the universe, right? And the math of the pull or the push works the same. It's an inverse R squared relationship. So there's this force that automatically happens through empty space between bits of mass and in here, bits of charge. The fact that this interaction seems to happen so fundamentally, the fact that this interaction seems to require no physical contact, no physical activity, no touching, and no action. In other words, if I put a proton here, just automatically, if there's an electron over here, they don't need to be touching each other to be pulling on each other. They don't need to be doing anything special to be pulling on each other. They just have to be there. They can pull on each other through any amount of empty space that's between them. And furthermore, if you put something in between them, like a desk or a piece of insulating material or anything, you don't block the interaction. The interaction just happens. It's fundamental, apparently. It requires nothing but the existence of charges for it to occur. And then when it occurs according to this equation that I just wrote, F sub E. F sub E equals 1 over 4 pi epsilon naught times Q over R squared. Now it looks, very ornate. Again, let me remind you, the 1 over 4 pi epsilon naught is just one big constant. That's just a constant of proportion. I mean, it's many constants, but put together make one big constant of proportionality. We write them in that weird way for reasons you will see. The R hat at the end of the whole equation is a vector symbol called the unit vector. I believe we established this last time. It can be intimidating or irritating at first, but it's establishing the direction of the pull or the push. And it just means that the direction of the pull or the push is along the line connecting one object to the other. Okay. So in the end of the day, what we're really saying is there's a force that one Q exerts on another Q that depends on the magnitude of each of the Qs and inversely depends on the square of the distance between the Qs, right? That's what we're saying about the force. But we're realizing that that is so strange. That is so strange that I can pull on you through empty space with an amount that depends on how far away you are from me in empty space. Like, it's so strange that the closer you are to me, the harder I'll pull on you, even though you're not touching me. Let me pause and say, why is that strange? I'll tell you why that's strange. Because it means that as I pull you toward me, if I'm a proton and you're an electron, as I pull you toward me and you get closer and closer to me, then apparently somehow I adjust my pull and start pulling harder on you based on the fact that you're closer to me now, but I'm never touching you. So if I'm adjusting my pull in response to how much closer you're getting to me, please think about this for a second. I don't think I said this explicitly last time. I just want to put in your brain this concept that if you believe in this force that we're writing down here, this force, fundamental interaction between 2 points of charge, if you believe that just like the fundamental interaction between 2 bits of mass, if you believe that this force can happen through empty space, but happens with an amount that depends on how much empty space there is between the 2 objects, then what that means is that each of the objects must somehow have access to the information regarding how far away the other object is. Let me just say that one more time. If I'm a proton and you're an electron, if I pull on you with a number of newtons that depends on how far away from me you are, then that means somehow physically I must know how far away from me you are. I don't mean know consciously. I'm not trying to be weird. I'm not saying think about. I'm not saying the proton thinks about how far away the electron is. But I am saying if the proton pulls on the electron with a number of newtons that literally is determined by the number of meters between the proton and the electron, even though they're not touching each other, then every time that number of meters changes and therefore results in a changing number of newtons, it must be the case that the proton receives the new location of the electron, right? That I must get updates as to your physical address if I'm going to adjust my pull on you in response to that address. That's a lot. You might want to think about that in your private Idaho. I mean, like we are saying that somehow protons over here know how far away electrons over there are. So how do we resolve this? Like, honestly, at the end of the day, I don't actually know how the universe does that. I don't think anybody literally knows how the universe does that, but the way we model it and the construct that we use to enable us to make predictions and do calculations and make sense of all of this is we say that the minute a proton comes into existence in the world, it creates a field everywhere around it. It creates a field which is all the information pertaining to it. All the information pertaining to it, all the information that would be calculated in a force, all the information except whatever information describes the second object that might come along and experience the force. The field of the proton is all the information that the proton would contribute to any force that it might exert on any electron that might come along and find itself at any point in space. So in other words, the field is the information of the force waiting to happen. The field is a bunch of vectors deposited everywhere in space, and at any point in space you name, there's a vector there whose length is the magnitude of the newtons waiting to pull or push on every 1 coulomb of charge that could land in a certain spot. And the direction of the vector is the direction that the 1 coulomb of charge that could be deposited in that spot will be pulled or pushed due to the original source charge. Okay, so field is force per charge. That's what we're about to calculate now. I'm just trying to, because it's been like a week and a half, I'm just trying to summarize this for you. Force is something Q1 does to Q2. Field is something Q1 does to every point in space. Force is measured in newtons. Field is measured in newtons per coulomb. The field that some source generates is the amount and direction of force that would be exerted on every positive 1 coulomb of charge that could be located at any point in space. Okay, and you could definitely put in the chat if you want to hear that again or if you have questions about that. But in the end of the day, field is, oh, this is supposed to be it. At the end of the day, field is force per charge. Field, this is net electrostatic force per charge. Force is newtons, field is newtons per coulomb. Field is what 1 Q does to the other Q. Field is what 1 Q does to space. The thing making the field is called the source charge. The thing experiencing the field ultimately as a force is called the test charge. Field is a vector. It has magnitude and direction. So what we're going to do in this problem now, what we're asking is, okay, if we're at, it's going to change the view on the screen here. If we're at the point 0, 0, we're experiencing a net, if you put 1 positive coulomb of charge at the point 0, 0, it would experience a net electrostatic force from both of those source charges that are in the situation. Whatever that force is, that 1 positive coulomb of test charge would experience at the origin, that's what we mean by the field at the origin. So what, okay, so we're going to add, so to get So to get the field, sorry, that was an interruption, but to get the field at 0, 0, we're going to add the contributing field vectors from each of those 2 points. We're basically, this is a problem in vector addition. Well, I'm just going to draw something. I'm going to pause for a second, but actually I'm going to pause for a second. Okay. So we're going to set, so I got to tell you again, like mathematically, once I set this up and we do this, it's a pure problem in the addition of vectors. The more comfortable you were with addition of vectors, like back in physics 203 with displacement vectors or velocity vectors, then you'll be comfortable with this. It's at least with the computation, but just like with velocity vectors, there was like doing it, and then there was understanding what it means. That's sort of the case here. So let me start by figuring out what these 2 vectors are. If you look at Q1, okay. I want to draw the direction of the arrow. Okay, I want to draw the direction of the arrow. Sorry, I'm totally. One thing I keep repeating, and I think I'm sure it's been overly repeated for some of you, but it might not have sunk in with others of you, is that the field is the amount of force that would be exerted on 1 positive coulomb of test charge. Like, right? So field is force per charge. And by the way, if you take that equation in your mind, field is net electrostatic force per charge. E is equal to F over Q. If you rearrange that in your mind, you have F equals Q times E. What that means is, if you know the field that you're in and you're like a little bit of charge and you're dunked somewhere in a field, as long as you know the magnitude and direction of that field, you multiply it by your charge and you'll know what force you are experiencing. Field, in other words, is how much force is exerted on every positive 1 coulomb of test charge. So if you put a 2 coulomb charge in a field, it will experience a force which is 2 times whatever the field is. The field is the amount that every 1 coulomb is being pulled or pushed. I don't know if that, but here's the part I want to emphasize right now. The field is how much we're pushing or pulling every 1 positive coulomb of charge. When we write out the field or when we picture the field, we're always, by definition or by convention, by agreement, we are expressing what would happen to a positive bit of charge if it were placed at that location in the field. Whatever would happen to a positive charge, the opposite would end up happening to a negative charge. But the field in other words, a field can be caused by a positive or negative. You see in this problem that we've got a plus 5 coulomb positive charge Q1 doing like, we got like a bunch of protons sitting there in the coordinate plane, but then we also have a bunch of electrons at this other location. They're each creating field. What I'm trying to, so a source can be positive or negative, but what the field does, when we talk about the field, we're talking about what we assume would happen to a positive charge. The test charge in our mind is always positive. What does all of this mean? It means that positive sources push out and negative sources pull in. We're talking about what we would do to a positive recipient. And like honestly, I remember I missed that for months in my first E&M class in college. Like I really missed that. And when it finally said, like it just, I hope you get that. So what I'm saying here is that Q1 is by definition pushing everywhere out of it. If I were to draw vectors of what it's doing, any point in space, I would draw okay, don't draw this. I'm just making a point here. I'm just going to draw this quick. I'll do this again at another point. But like what Q1 is doing is for every point in space near it that I picture, for any, this is the idea of a vector representation of a field. Don't draw this, just look at it for a second. I mean, you could draw it, I suppose, but do you see the idea behind this is that those are just representative vectors. The truth is there's vectors everywhere going on everywhere in space, but the idea is any point in space you pick, there's a vector that's pushing away from the original source. And as you get farther and farther away from the source, the vectors get shorter and shorter, right? But they're always along these radial lines. Can I just get like a quick electric thumbs up if you sort of understand what I'm saying about the field? A field is an array of vectors everywhere in space. A field is a function. The input is location in space. The output is vector representing force per charge. So if I say that the proton creates a field, I mean that everywhere in space, there's a little vector pointing away from that proton. And as you get farther and farther from the proton, the vectors get smaller and smaller. Can I just get little electronic thumbs up or something if you I'm not asking you to do a calculation yet, but just can you picture what I just, oh, I got it. Okay, I seen it. I didn't see them before. Okay, great. Thank you. That makes me very happy. Okay. Okay, so what does that mean? So those red lines that I just drew, they're accurate. The reason I said don't draw them is they might just confuse your, like, you're not going to use all those red arrows. They're just to picture what's going on from that source. You could draw a bunch of similar red arrows all radiating in toward the Q2, because it's negative. Positives push out, negatives pull in, because we're talking about what we would do to a positive recipient. All of that is to say, I believe then, I guess I'll leave those arrows I hope they don't confuse, but I believe then there's a vector that is pointing from the Q1 to 0, 0. There's a vector pointing like this, like at 0, 0. If there was no other charges in the world, there would be a field vector going down and left from at point 0, 0. And the length of it we would get by plugging into that equation, and the direction of it would be literally this direction along the straight line connecting the two, right? And that would be it. That would be the answer. But there's this other charge in the world. There's this other charge, Q2. It's affecting everywhere in space, including the origin. What is it doing to the origin? Well, on the origin, it's pulling out. It's pulling, right? Because it's negative. So there's this arrow on the origin going like this. You see what I'm saying? And our job in a minute, if I ever stop talking, our job in a minute is to add those two vectors together to get the full field vector at 0, 0. Part of what I'm trying to say in this whole buildup or in this whole diagram is there's nothing special about the point 0, 0. That is just what I call the location of interest. Like everywhere in the world, there is field due to the two charges. Everywhere in the world, there's a new vector now that is the sum of vectors pointing to it from Q1 and Q2. But 0, 0 just happens to be the location that we're interested in. I call it the point of interest. Textbooks and websites will tend to call it the field point. You can call it that too. I mean, we all call it point P. You can call it the field point. I just don't love that because it makes it sound like somehow it's a point that especially has field, and all the points have field. It's just the point at which we are trying to calculate the field is what 0, 0 is. So we're going to add those two vectors together, okay? But one is pointing down and left, one is pointing up and right. So, okay, we need to add vectors. We need to add the vectors E1 and E2. So now to be careful too, if you remember from physics 203 and so forth, like if we're adding vectors, that means we can always move vectors wherever we want. The information of a vector is its size and its direction, not where it is on the page. So if we want to add vectors, we shift them so that they're tip to tail, right? So in principle, we're going like we're adding two vectors like that. Like that is definitely not to scale, but that's the idea. And the answer that we're going to get, I'm doing this very much not, will be the final vector that points from the original tail to the final tip, right? That blue arrow is our answer, our total field. Okay. Just looking at. Yeah, I mean, and this, this is definitely not drawn to scale. Okay, so we're adding those two vectors together. So how do you do that? You have to add by components, right? So that's what we're going to do. If you want to actually get answers. By component method. So this is what we spent time doing with displacement vectors and then velocity vectors and even to some extent with projectiles and stuff. And then with forces in physics 203, it's a technique that works for the rest of our life with any quantity that is a vector quantity. So we're going to add vectors by the component method. What do I mean by that? I mean, we'll take one vector at a time. We'll take the first vector. Whoop, hello. We'll take the first vector, the vector from Q1. The vector from Q1. Move it now. Okay. So let me just scale this better. I'm sorry. This vector is okay. This is the field contribution from the first vector from Q1. Now, what do we know? And we know that Q1 is at the point 5,4. We know that the origin is the point 0,0, and we know that Q1 has a charge of, I believe, plus 5 coulombs. Right. Okay. So we know, if we call this angle θ1, we know that the horizontal leg of this triangle is 4. Is 5. We know that the vertical leg of this triangle is -4, right? We know that this vector is going left and down. Why left and down? Because it's pushing out from Q1 toward the origin. So it's going to the left and down. So it's going negative in the X direction and it's going negative in the Y direction. So let's look. So what we want to do is get the horizontal component of it and the vertical component of it. And then we want to get the horizontal component and the vertical component of the other force. And we want to add the other field contribution. And we want to add the horizontals and add the verticals. So the horizontal component of this field contribution, the horizontal component is that constant times the charge over the distance squared, right? Like that, I'm applying the definition of field due to a point charge. The field due to a point charge is the constant times the charge divided by the distance squared. And then yes, times that r hat thing, but I'm just looking at horizontal components now. Like I'm just looking at components of vectors. I'm not looking at the overall vector. So I'm not going to write in that r hat thing. But if I want the horizontal component, I want the whole magnitude times the cosine of that angle, right? I'm looking at the horizontal component, like just to remind you, I guess, like if you just have some random vector, if you have some random vector v, then the horizontal component is v cosine theta, and or at least the adjacent component is v cosine theta, and the opposite component is v sine theta, right? So I'm just doing that right now. And I'm obviously going to fill in numbers in a moment. But what is cosine of theta? Cosine of theta would be adjacent over hypotenuse, right? So it would be, well, here, sorry, I'm going to start filling in numbers on the next page here. So on the next page, E1x equals that constant. What is that constant? That constant is approximately 9 times 10 to the 9th Newton meter squared times Coulomb squared. Right, it's 8.99 times 10 to the 9th, but you can round. I think it says on the sheet. Q1 we said was 5 coulombs. R squared is what? Well, it's 4 squared plus 5 squared. I'm doing that Pythagorean theorem to get, right? R, the hypotenuse, is the square root of the x squared plus the y squared. And then what's cosine of theta? Cosine of theta is adjacent over hypotenuse. So it's 5 is the adjacent, and the hypotenuse is square root of 4 squared plus 5 squared. Do you see what in fact, it's 110. Yeah, I'm going to pause for a second. Look at that and tell me if you understand where I just got. If you understand that, I'm going to do a bunch of repetitive things from here on in. Someone just came. Okay. I'm going to do a bunch of repetitive things from here on in, but I really stare for a second and tell me if you understand where I just got all those numbers. Honestly, this is for the x component, the horizontal component of the first field contribution. Because even if we run out of time, I'm going to tell you right now, we get the x component of the first field contribution and the y component. Then we get the x component of the second and the y component of the second. And then we add together the x's and we add together the y's. And we make one big triangle out of that one big right triangle, and the hypotenuse of the big triangle will be our answer. I mean, that's a procedure I'm doing here. We have 20 minutes. I mean, this is from here on in, it's a thick computation, but there's no new concept or anything. So and you do want to know this. So I'm going to look again at do you honestly understand where I just got those numbers? Thank you, Jalen. I totally appreciate it. Thank you, Stephen. I totally appreciate it. I'm going to go. Thank you, Ashley. Thank you, Brianna. Okay. And does anybody want to put in the direct chat that they don't I mean, this would be the time. There would be no shame in not understanding something I just did. But now I'm going to ask you to be with me. So, and thank you, Abdel, and thank you, Brooke. All right. So I'm going to just pause for, if you put something in the direct chat, I will not criticize you or shit. It's like, seriously, you want to pause for a second and make sure? Okay. I'm going to keep going with it. All right. Okay. So, and I'm also pausing a lot because in case we run out of time, I will hope that you'll know how to put this all together, even if I don't finish, because that's the program. But okay. So I'm going to fill out, and in fact, the units, I'm not even going to worry about the units for the moment. I'm even going to round a little bit more. I'm going to, just to make this picturable, 9 times 10 to the 9th, I'm going to round to 10 times 10 to the 9th. In other words, 1 times 10 to the 10th. Okay, just so we can really picture this. So we have 5 up here, and we have 16 plus 25, right? 16 plus 25. So that's 41, right? And hopefully you see why the 4 squared plus 5 squared is not square rooted at first, but then it is square rooted. Like, that's not a mistake. Ultimately, we have r to the cubed, if you're really following this. Like, this is what we have so far, right? And I'm rounding so that we can get some perspective on these numbers. Right, and now square root of 41, that I cannot do in my head. I'm not going to pretend to. And you should also, if you're following this, if you're not following it, please try to follow it and please be honest. If you are following it, check my numbers, please, and put in the direct chat. If not, what just happened? Okay, so what I think we have so far. In fact, to be even more clear, what I'm saying is well, when we write symbols without the vector symbols, we're just talking about magnitudes, but to make it really clear, that's just a magnitude, 9.5 times 10 to the 8th newtons per coulomb is the horizontal contribution of the first field. And if you look at the diagram, honestly, I would say that is negative because it's going left. Okay, so now we go, it's 115. So now we do the exact same thing for the vertical contribution. The exact same thing. Well, it's 1 times 10 to the 10th. I'm going straight to the rounding. 1 times 10 to the 10th times that same charge, which is a charge of 5, over 41 times the sine of the angle now. So the sine of the angle would be 5, would be, would be 4 over the square root of 41, right? So it's going to be 1 times 10 to the 10th times 20 over whatever the number is, over 263. And right, I'm just doing the same thing I did a second ago. But now also, if I look back at my diagram, this vector component is pointing down. It's also negative. I mean, assuming our coordinate system where no. Okay. Thank you, direct tap person. Although I think he's already. Okay. So I have this. I think this is also negative because it's going down. Okay, so now I have the two components of the first vector. Presumably on your own, you could do the other. I'm going to do this so I can complete the problem so we can all have clarity. But I hope, again, if you think you're following this, you might want to just stop listening to me for a minute and try it on your own. but if not, not. So now I go to the E2x. E2x is now same thing, 1 times 10 to the 10th times the other charge. The other charge, I believe, was given as what, negative, oh, I should draw it, I'm sorry. But the other charge is given as -2, and it's at 10.3. Okay, here's the other charge, I should draw it. So here's now. This one is this one pulls, right, to a -2 charge. It pulls and it's at the coordinate 10,3, I believe, right? So it's pulling like that. This is theta 2, right? This is the other charge. Check one more. Yeah. Okay, so if we're going to calculate the components of this, then E2x will equal 1 times 10 to the 10th times the charge. What is the charge? The charge on this one is 2. And notice I'm not putting in the negative signs or the positive signs until the end. Like I'm looking at that. I'm taking these vectors seriously. I'm looking at tips and tails to tell me negatives and positives, and I'm using negatives and positives to determine the tips and tails. But I'm not double counting myself. So I'm not putting in a negative in the charge here because I've already taken that into account when I decided that this arrow was a pull rather than a push. I hope that's clear. So the charge is 2. The R squared is 10 squared plus 3 squared, right? And then all times cosine of the angle. The cosine of the angle is 10 over the square root of 10 squared plus 3 squared. Again, stop me if you're not seeing where I'm getting these from. I'm just repeating the pattern of the other charge. And I'm assuming my numbers are right. Yeah, 10 and 3. Yes. Okay. So now I have 1 times 10 to the 10th. That's rounding. 20 over 100, 109, right? And so that's 138. Okay. Okay. We're just about there, 9 minutes. So this is the horizontal component of the second field contribution, and it, according to the picture, is pointing to the right, so it's positive, right? And then finally, we're going to do the y component of the second field contribution. This one will be 1 times 10 to the 10th times times 6 over 1138. Where did I get 6 from? It's 2 times 3 rather than 2 times 10. It's the y coordinate over the hypotenuse rather than the x. It's opposite over hypotenuse rather than adjacent over hypotenuse. And that's the only distinction, right? So we get 5.27 times 10 to the 7th. This one's much, much smaller. That makes sense. Yeah, I mean, the y component is a much, much smaller contribution. And this one's also positive because it's pulling up. So now what do we do? And I know we only have 7 minutes left. Well, oh, yes. Thank you I'm so glad. Okay, someone in direct chat just asked me to repeat why it's 6. It makes me so happy when people do that because it's showing that you're totally paying attention. And yes, that part, I would want that part repeated as well. Why it's 6 instead of way up above, way up. Oh, maybe I'm wrong, actually. Wait a second. Yeah, it's 6 because way up above, if you compare the very first line on the sheet here, you see that I have 2 times 10. Like it's 6 instead of 20 because way up above, I have 2 times 10. The charge was 2, so that stays the same. But the 10 was because 10 is the x coordinate. 10 is the adjacent side that we're putting over the hypotenuse. Where this whole thing right here is adjacent over the hypotenuse, meaning cosine of the angle. But now we're trying to do this part here. So this is cosine of the angle. But now we're trying to do sine of the angle. So we're trying to do opposite over hypotenuse. Okay, great. Okay, so you got, okay, great. So it's, yeah, so to anybody, I'm so glad someone just asked, and I'm glad that, and thank you for responding in the thing. So yeah, to anybody else who's still listening and I just cut myself off, it's 6 because it's 2 times 3 instead of 2 times 10. 10 and 3 were the x and y coordinates of the, okay, but thank you for asking and thank you for acknowledging the answer. Wait, let me do something else in the chat. Okay, great. Thank you. No, thank you. Okay, and we have 6 minutes. Okay, so we're almost done. What do we do now? Now we we make an XY chart, just like we used to do with velocities in physics 203. We're literally making an XY chart, adding together the two fields. So we have, so EX1, so 9.5 times 10 to the 8th. We have 9.5 times 10 to the 8th negative. And then we have 1.76 times 10 to the 8th positive, 1.76 times 10 to the 8th positive. And in the Y's, we have in the Y's, we have negative 7.6 times 10 to the 8th. And positive 5.27 times 10 to the 7th. Again, that's a very small contribution because that triangle is so lopsided. I mean, that second triangle is so much wider than it is high. Okay, so we're literally now adding together these contributions, adding them because we're adding together two vectors. We're adding them, but we're taking into account the minus signs from directionality. So we have negative 7.74 times 10 to the 8th is the total X, and the total Y is negative 7.07 times 10 to the 8th, I believe. You should check me on that, but it seems right to me. Because it's a very small. Yeah. Okay. So we have 3 minutes left. We're just about done. What do we do with this piece of it? So that's our final EX and our final EY. And they're both negative, right? So that means that our final field is pointing something like this. And they're pretty similar numbers. So it's doing something like this. Oh, no, I'm lying because sorry. So stupid. They should both be negative. So it's doing something like this. I promise we're just. So we draw an X to the left, and then from its tip, we draw a tail down, right? We're doing tip to tail, and the EY is this. And the sum is our answer. Like our total E vector equals, we have 2 minutes left, equals, so I'm not going to, equals the Pythagorean sum of those two numbers. Right, it's all 10 to the 8. Our final magnitude of the vector is the Pythagorean sum, square root of the squares of those two numbers. I'll let you do it because I'm going to like freak everybody else if I do. And our final direction is the arctan of the opposite over the adjacent. And there you definitely don't need the exponents. So that I'll do really quickly. We're just about done, I promise. Something like 42 degrees southwest because negative, right? I think it's 42. I might have just done that too fast. I know we are just about to go, but I just, as long as we're doing all this. Yeah. Yeah. Okay. So these two numbers, the final E and the final angle together make the final answer. We're saying at the point 0, 0, there is, for every 1 positive coulomb of charge that could be found at the origin, it is pushed down and to the left with a strength of approximately, 8 newtons, 8 times 10 to the 8th newtons. That's what we're saying. It's a vector addition problem. Okay, you've been very patient. I'll stop with that for now. There's no new homework. Just try to incorporate this, ask questions on whatever next week. See you next week. And I'll see you in my office next week. Okay, thank you.
Have a good day.
Thank you and have a great day.
You too. Thank you. Thank you. You too.